Hello, welcome. Let's see if we can't get you ready for a test coming up on Chapter 5. Chapter 5 was a short chapter about inequalities. How about a little review here? Can you name some inequalities that we learned in this chapter? Name a couple of them, see if you can get the ones here. Pause it, give it a try. All right, you're back. Hope you challenged yourselves. This is what you'll need to know on a test. If two sides of a triangle are not equal, there's an inequality. The angles opposite them are not equal in the same order. Then, of course, if two angles of a triangle are not equal, these sides opposite them are not equal in the same order. We also had an exterior angle of a triangle is greater than either remote interior angle. That, of course, is a theorem about it. It's not the definition. The definition is it's an angle that forms a linear pair with an angle of a triangle. And then we had this triangle inequality. The sum of any two sides of a triangle is greater than the third side of the triangle. So as we get going into the review here, we're trying to remind you of some of the things found in this chapter. First one maybe is more fun than anything. Sam Lloyd is a famous I don't know, puzzle creator. He has a lot of puzzles out there that he did. And here was just a cute little one. George Washington. Not only did he cut down the tree here, he's hiding in the tree. I don't know if you can see him or not. I don't know if that helps looking at this angle. Here you see him. Nose, mouth, eyes, hair, fancy collar. And here's the point. How do you have to view the picture to see him? At a different angle. At a different angle. Mohs scale tells you how hard a mineral is and what it will scratch. And here's the key. Read this sentence. Diamond will scratch quartz and quartz will scratch glass. What conclusion seems to follow from this statement? Diamond will scratch quartz and then quartz is going to scratch glass. Seems pretty clear that diamond then will scratch glass. And they want to challenge you with what property is that like. So look back through the properties and find which one that mimics. I was here once. I don't know if you were here or not, but it's kind of neat. You can jump into a conveyor or kind of an elevator, I guess you can call it, and you can make your way all the way up to the top up here. Right now we're looking at the width of the arch and the height of the arch, and we're asking which property of inequality names the ways in which the height and width might compare. Look back through those properties. Now it's just an eyeball. How do you think the height compares to the width? And I took that picture and put a line segment there, brought it up and flipped it, and boy, it's pretty close. Pretty close. Measure the dimensions. Use the fact that 1 inch is 252 feet to get the actual height and width of the gateway arch. So a Portuguese theorem, we can't read Portuguese, at least I can't, but I can guess at some of this. It's from a geometry book, so that's probably theorem. This word looks like angle and then externo. That sounds like external, exterior. So maybe that gives you a hint as to the theorem. Triangulo, that looks pretty obvious. Angulos, internos, adjacent to, not adjacent. So which theorem do you think this is? And write it out in English in a complete sentence. And then we're looking for the definition of an exterior angle. Now a question, what can you conclude about the angles of a triangle if the exterior angle is 1 degree? Maybe that picture helps you. Some conclusions, what could you say about any of the other angles? You could say a couple of things there. What if you have an exterior angle that is a right angle? What other things can you say? Try to go for more than one thing. What if the exterior angle is obtuse, like this one? Right in here we have an obtuse exterior angle. what else can you say? All right, next couple sections here are about soccer and about goalkeepers. You call them a goalie, goalkeeper. So here's the strategy. Keepers utilize their geometry skills. Yes, it's there even on the pitch. Another tactic called cutting the shooter's angle. You want to make it as hard for the kicker to score as possible. The goalie imagines a straight line between himself and the ball and the middle of the goal. So the shooter always has an equal amount of goal to shoot at from both sides. You don't want to give him a nice wide spot. So if this is the shooter, and there is the goalkeeper, and here's the goal, the left and the right side of the goal, the idea is to keep these angles right here the same. So right here we've got some givens, it looks like. The shooter is centered, so SL right here is equal to SR. So I want to keep that in mind. Draw the figure and mark it. We know one other thing here. M is the midpoint of LR, so that helps us. I'm going to go ahead and put 2 lines on this one and 2 lines on that one, which we know to be true. Now give a reason for each of the following statements. LM equals MR. Well, we just talked about that. Why do we know those have to be equal? SM is SM. So you know a reason why anything's equal to itself. So they're going right to congruence here. Hopefully you can come up with that reason just looking at that picture. Now they're saying angle 1 and angle 2 are equal. These 2 angles down here. And they're saying that angles 3 and 4 up here are also equal. We'll put 2 tick marks on those. What's the reason for that? And then finally, a little bit trickier, SM perpendicular to LR. So now they're looking at, let's get rid of something down here. Now they're looking at this spot right here, and they're suggesting that these 2 lines are perpendicular. You got to pull a theorem out of the hat from back a ways. Keep in mind what 3 and 4 are, and what's true, that fact that those 2 angles are equal. We're moving the shooter over here on an angle, so the givens are just a little bit different here. We know that SL is less than SR, so this is a given. He's closer to the goal on that side than he is to this side. So draw the figure again and mark it as needed. This is still the midpoint. Remember, it's that line between the shooter and the midpoint that the keeper stands on. So I think we can mark these 2 the same. Whether that helps us or not, I know it's true. So angle L greater than angle R. How do we know that this angle right here, angle L, is greater than angle R? Well, take a look at the given, call to mind a theorem. Now they're saying that angle 4 in here is greater than angle L. Angle 4 is greater than angle L. That's out there with 2 lines on it over here. So I'm going to put 3 lines on here. So why would angle 4 be greater than angle L? And now take a look at 22 and 23 and see if you can get a reason why angle 4 would have to be greater than angle R. And then finally, why is SR greater than SM? Well, we always have to ask yourself, if 2 sides of a triangle are not equal, what must be true? Well, the angles opposite them must not be equal. So look at number 24 here. We said angle 4 is greater than angle R. That means the side opposite angle 4, which is SR, has to be greater than the side opposite angle R, which over here is SM. So there you see it. So that gives you the answer to this, the theorem that says if 2 angles of a triangle are not equal, the sides opposite them are not equal. This one is similar to the problem we had with that building that the architect designed, where the floors were a little bit different. Here we've got a column and we've got little sections that are different heights. They want you to take your protractor and put it right here at C. I guess I could draw a little picture here. So put your protractor there with the point, the center of the point at C, right here. And what do you notice about the angles formed by the lines from this point? So they're looking at these angles. Use your protractor. And what do you notice about those angles is the question. What do you notice about the lengths of the sections of the columns? I mentioned that already, like 1, 2, 3, and so on. Why do you suppose the column might have been designed this way? And finally, taking a look at these. Why is angle 1 less than angle 2? If you don't see it right away, you might have to realize that this, oh boy, this is going to be tough here. Here's a triangle. Yes, that's a triangle. This is angle 1, and here's angle 2. So now, can you answer why angle 1 would be less than angle 2? Kind of messy, so we'll get that out of there. Maybe that helped. And angle 2, why is that less than angle 3? So we're looking right in this area here. Why is 2 less than 3? And then finally, again, why is 1 less than 3? Take a look at 29. He's trying to get you refamiliarized with one of the properties we had. Moving on to set 2. So number theorem here. 1, 3, and 5 are consecutive odd integers. They're not even, they're just odd, but they're the ones that would come right in order. 1, 2, 3, 4, 5. 2, 4, and 6 are consecutive even integers. Not a hard thing. The figures below show the results of trying to construct triangles with these numbers as their sides. These numbers over here as their sides. So there's the first one with 1, 3, and 5. So there's a length of 1, and there's 3, there's 5. You can see they were not able to create a triangle. Maybe you can already tell why that is. There's a 2, 4, and a 6. Again, maybe you can tell why that won't quite work. Yeah, what if you move D way over here, though, so that the 2 was slanted this way and the 4 going this way? Wouldn't that work? I think you probably know the theorem that's happening, and explain in each case why no triangle is possible. No triangle is possible. Look at the lengths of the sides and find the theorem that works with that. D, E, and F, how are they related? What does it look like? What does it look like there? Try to construct a triangle GHI, so that's new letters, whose sides are consecutive odd integers 3, 5, and 7. So maybe take your ruler and maybe your compass to get the lengths, or just take your ruler and lay it out there. Do you think you'd be able to make a triangle with 3, 5, and 7? That's the question. So now they try to go to general terms. If n is an integer, then n, n plus 2, and n plus 4 are either consecutive odd integers or consecutive even integers. 2 plus 2 is 4, 2 plus 4 is 6, and so on. From the triangle inequality theorem, we know that if n, n plus 2, and n plus 4 are sides of a triangle, then what has to be true? Triangle inequality. The sum of the lengths of any two sides of a triangle have to be greater than the third side. So we could write that this way, that n plus 2 has to be greater than the third side, n plus 4. I'm guessing the algebra in you says, oh, we got to solve that one for n. That's what he'd like you to do here right away. So how does that work? We've got 2n over here plus 2 is greater than n plus 4. So what do we do with the algebra here? Not too easy with the mouse. So I've got a plus 2. I'm going to subtract 2 from both sides. Okay, and I've got an n here, and I've got 2n there. So I'm going to move this n over to there. I'm going to subtract n from both sides. So we do end up with n is greater than 2. Now, do you think you could make a triangle that was 1,000,000, 1,000,002, and 1,000,004? n, n plus 2, n plus 4. Yes or no? Think about that. As the numbers in a set of consecutive odd or even integers like this, as they get larger and larger, we're up into the millions here, what does the triangle having them as sides look more and more like? So picture this triangle. It starts to resemble something else. So here we have a base of an isosceles triangle. It's the unequal side. The base of an isosceles triangle is the unequal side. That definition's a little different than the one we've been working with. Base is the unequal side. That's telling you that there's at least one unequal side no matter what. Whereas our definition says an isosceles triangle has at least 2 equal sides. This wouldn't allow for that, would it? So let's take some questions here. If an isosceles triangle has an unequal side, how many unequal angles does it have? If it has an unequal side, say it's this bottom one, that means these two must be equal to be isosceles. So how many unequal angles does it have? Continuing, how does the statement disagree with our definition of an isosceles triangle? I just kind of told you that one. Is an equilateral triangle isosceles? Well, depends on how you look at it, doesn't it? You decide which way you want to look at it. So there is an equilateral triangle. Is it isosceles? All right, here's 2 triangles. If one side of an isosceles triangle has a length of 10, what possible conclusions can you draw about the lengths of the other 2 sides? So pause and think about this a little bit, and then when you come back, we'll see if you agree with me. All right, so hopefully you paused. So if one side is 10, what can you say about these other 2 sides? Now it's isosceles. Boy, that's aggravating. It's isosceles, so we know these 2 have to be the same. But actually, what size could they be? Ask yourself that and see if you can figure that out. Now here we assumed the 10 was the unequal side they were talking about. Is it necessarily the unequal side? What if the 10 is one of the equal sides? Now what conclusion can you draw about the lengths of its other 2 sides? So think about both of those situations. Figures below show a ball as it moves from one position to another on a stereoscopic screen display. That's a display where they try to make things look 3-dimensional, give it depths. On an actual display, the ball appears to be in front of the screen in the first figure, but behind the screen in the second. Huh, that's kind of neat, right? Well, let's look at a diagram of how they're actually doing that. This is an overhead view of somebody looking at a stereoscopic display. Only works if this ball here, this blue ball, is completely in the shaded in area. Otherwise, it's not going to look quite right. So let's use this figure here. We've got the screen, we've got the left eye and the right eye, and we're trying to look at this screen. Now we've got some givens up there. Let's see if we can't mark those. LA equals RB, so I can put these 2 equal. LB, so this one that runs through here, is equal to RA, this one that runs through there. Okay. And then finally we know LB, LA equals RA. Now we know LB is greater than LA. LB, okay, so that works. This one here, LB, is greater than LA, and I've got 2 tick marks on that. So that one's bigger than LA up here. Okay? Let's go with that now. They've got us going right to congruent here. Can you see it? See if you can figure out. Now, I got a little messy right here, but we've got 2 tick marks here. You have congruence. What's the reason here? Well, remember this. It's in both triangles, so that'll help. Angle LBA, LBA, that's this one, is equal to angle 2 is the suggestion. Okay, why would that be? Well, B is in this triangle LAB, and 2 is in this triangle RAB. And take a look at this. It should give you a pretty good hint. All right, we're back to this. Angle LAB, this angle down here in the corner, is equal to angle 1 plus angle 2. I hope you're getting close to where you're recognizing that. I think many of you are. But if you have a ray between two others, remember what happens. LAB is greater than 2. So now they're saying that that entire angle, that whole angle, LAB, is greater than angle 2. What's that reason here? Number 44. Number 45, now we're saying LAB is greater than LBA. Well, here's our LBA greater than, but here we've got an angle 2, and here we ended up with angle LBA. Can you find a reason why we can go from 44 to 45? And now that we've got angle LAB, this whole angle right here, greater than angle LBA, this smaller angle down here, so we've got this one greater than that one. Now they're saying LB, this guy, is greater than LA, this guy over here. Should have that by now, I hope. All right, one of my favorite problems, SAT problem. A triangle has lengths of x, x minus 2, and 7 minus x. Write 3 inequalities for this triangle that follow from the triangle inequality theorem. So there's a triangle out here. So one of the sides is x, let's call it this one. One of them is x minus 2, and one of them is 7 minus x. All right, so write 3 inequalities. And from them, what can you conclude about x? How big is x? Show your reasoning. This is a good problem. So here's one of the inequalities. See if you can write the other 2. I've got one side plus the other side is greater than the third side. Do pause this, please, and give it a shot. All right, here are my other 2. Oh, I guess I solved this one first. So I've got minus x plus x over here, so 3x is greater than 9. So I had minus 2, looks like I added 2 to both sides. So x ends up being greater than 3. So in that triangle on the previous screen, the x has to be greater than 3. Can't be 1 or 2, greater than 3. If you do another one of the inequalities, however, this side, x, plus this side, 7 minus x, has to be greater than the third side. Triangle inequality. Solve that. X minus x goes away. We've got a 7 here. X minus 2 plus 2, so 9 has to be greater than x, or x is less than 9. So now we have x is greater than 3, but we have x is less than 9. You picturing that? But we have a third set of sides to work on. So now we've got this x minus 2 side plus the 7 minus x side has to be greater than the x. Your algebra, the x's go away. This is a 5. Minus 2 plus 7 is minus 5. So that one solves right out here to x is less than 5. So try to put all of these together and tell us what x could be. Well, I can see it can be greater than 3. So it could be 4, 5, 6, 7, 8, 9, 10, and so on. But here we see it's got to be less than 9. So it can be 4, 5, 6, 7, and 8. But here it says it has to be less than 5. So it could be 4. It can't even be 5, can it? So it must be, if you're just thinking integers, it must be 4. If we chart this, graph this, so it's got to be, it can't be 3, it's got to be greater than 3, but it has to be less than 5. So it's these set of numbers in here. If it's an integer, it's going to have to be 4. If it's not an integer, it could be anything greater than 3 and less than 5. Fun problem. Okay, so we're into proofs here now. Got some proofs to work on. We're trying to prove that A plus C is greater than 90 degrees. A plus C greater than 90. And from the picture, I don't know how we would get there. We know that if you add these three together, it's 180. If one of them was 90, we'd be all set. If B was 90, then we'd know A plus C is equal to 90. But we don't know that. So let's take a look at what we do know. AB is greater than AC. Doesn't really look like it on the picture, but that's what's given. And angles A and B are complementary. Well, what do we know about complementary angles by definition? That's kind of nice that the complementary angles, their sum is 90, and that'll get our 90 into this proof here somewhere. We've got to get a 90 in there. And they're saying A plus C greater than 90. Well, let's just go with what we have and see what we can do. We're going to start with A and B are complementary, and the reason over here, it's really good if you try this on your own, but yeah, that's given. Now, this idea of complementariness, what would be a logical next step? To go ahead and say that their sum is 90, and that would be the definition of complementary angles. Okay, now what do you want to do? We can't go much. We've got A plus C is greater than 90. Here we have A plus B is equal to 90. So we got to do some switching here somewhere. Let's go take a look at the other. Oh no, we're going to do one more thing. We're getting B equals 90 minus A. This is kind of a tricky step. And maybe we do this because we have a C and a 90 up here, but we don't have an A. I'm sorry. Yikes. We have an A and a 90, but we don't have a B up there at all. So I guess the idea is let's try to get those ideas into the proof. And you'll see this is just subtracting angle A from both sides. Now let's head up to the given up here. That angle A and angle, that AB is greater than AC. So we just do that given. Well, now what do we know if two sides of a triangle are not equal? Finish that in your head, I hope. Then the angles opposite them are not equal in the same order. So we should be able to say that angle C is greater than angle B. And that's what we're doing in the next step for that reason. If two angles are not equal, the sides opposite are not equal in the same order. Okay, so now what are we doing? Let's take a look here. We've got AB is equal to 90 minus A. We've got C is greater than B. So what do you want to do with that? C is greater than 90 minus A? Well, that's nice because we've got our three components here then, just not in the right order. What's the reason for this step? How do we get from here? Look at the left side. That didn't change. Look at the right side. We went from angle B to 90 minus angle A. Yep, you can see it right up here in number 3, right? So that would be substitution. Steps 5 and 3. And then we go to the proof step that C plus A is 90 degrees. We're just rearranging here a little bit, aren't we? We're probably adding angle A to both sides. So there's that first proof. Okay, the last proof. Take a look at this, see if you can figure this one out. On your own pause, consider it for a bit. What do we have here? We have X on the side of AC. XB and XC are equal. Well, that helps me a little bit. I see that if two sides are equal, then these angles here would have to be equal, B and C. What are we trying to prove? We're trying to prove that AC from here over to here is greater than AB from here over to there. This is a great one to go backwards on. to say, well, if our last step is AC is greater than AB, the step right in front of it, we're going to have to try to say that two angles are not equal. Which two angles? Well, if we can get this angle up here, ABC, to be greater than angle C, then the sides opposite, AC, has to be greater than AB, and that's what we're after. So if we can get that to happen, we're in good shape. So we don't have a reason yet, so let's work our way back up to the top up here. And let's start. XB is XC. We just pull that out of the given. And we said, well, if two sides of a triangle are equal, yep, the angles opposite them are equal. Now here's one we've been going to the well quite a few times on this one. Betweenness of rays theorem. We're looking up here. Can you finish that one? Challenge yourself. Angle ABC is equal to angle XBA plus angle XBC. It's the betweenness of rays theorem. Now, are we close? We've got ABC here, we've got ABC there. We need a greater than angle C. Well, you know what? This is the whole angle, isn't it? Let's use the whole greater than part on it. Angle ABC is greater than, which one do you want to choose? We're going to go with XBC, XBC, because we were trying to get this angle and this angle. We know something about those, don't we? So we can substitute steps 2 and 5. I wonder if I meant 4 there. Probably 4, because C is XBC, and there's XBC, so we're going to substitute the C in for that. And now we're all set, because now we know that if two angles of a triangle are not equal, the sides opposite them are not equal in the same order. If you happen to be watching this, then you'll see there are some proofs here that we probably won't have in class. Can't remember for sure, but there's some challenges for you to look at. You'll likely see those on test, so you can take some time and give those a try. We will see you in class then today, and if you have any